Okay, we're going to go into a little bit of detail about the math and the coding now. We did a kind of overview of backpropagation. We're going to go into a little bit more detail here. First of all, just a word about the terms downstream and upstream. So we talk about this as the first layer, second layer, third layer, and the input comes in here and gets output here. So this is called downstream. And when we're talking about upstream, we're talking about going from the right to the left. So downstream is left to right, and upstream is right to left. So let's look at this a little bit more carefully. We're talking about the calculation of dj, dw2, and this is for the 111 network. In other words, for this network here, we call this the 111 because there's one node in the first layer, one node in the second layer, and one node in the third. So this is the simplest one that we can look at. So let's consider the derivative in that case. The derivative of j with respect to the W2, which is the, I guess I could say it's the most downstream set of weights. So actually, this is the derivative using the chain rule, and I think we talked about that a bit. So this is the derivative of j with respect to W2, and this is the derivative of j with respect to W1. And you can see basically that this is a bit longer than this one, and that's, as we said, because you have to go through more steps from j to get to W2. I'm sorry, more steps from j to get to W1 than you do to get to W2. W2 is closer to j. However, in the book we note that if you look at both of these, you'll see that they have quite a bit in common. This has this term and this term are the same. The next term and the next term are the same. This and this are the same, and this are the same. So those four, I think it was four terms, are the same. So we're going to filter those out and call, we're going to call these four, we're going to call them delta with a 3 to indicate that this is kind of, to indicate basically that stops here. The next one is going to be called delta 2, and it's going to indicate that it stops here. So this delta 3 has 1, 2, 3, 4 terms in it. And this derivative has 1, 2, 3, 4, 5 terms. The first four we're just going to call them delta 3. That's all that delta 3 really is. But in that case, then we can rewrite this as delta 3 times the last term. And the last term is the derivative of z3 with respect to W2. So let's look at that. Let's think about that. Let's just repeat it first of all before we go to the picture. The derivative of z3 with respect to W2. Now W2 is just to the left of z3, as we'll see in the picture. So W2 is just to the left of z3, and we're talking about the derivative. It said the derivative of z3 with respect to W2. So without me writing this, I'm not going to write this, but what is z3? See, this is a simple calculation because this is a simple network, and z3 is just this times that. So z3 is this times this, and if we take the derivative of this times this with respect to W2, that means that we just get A2 as the derivative of that. So that means that the derivative that we just mentioned is going to be this A2. Now maybe we've written that more explicitly on the book, so let's look for that. But you can see it visually here. The derivative of z3 with respect to W2 is this, because this is simply this times this. So if I take the derivative of this times this with respect to this, I just get that. So first of all, here's the expression dj dw2 is the delta times this. And then I just said that this is just A2. this part here is just equal to A2. Okay, I just typed this in here. I don't want to deal with subscripts, superscripts rather. I guess I could easily make this a superscript. I'm not going to bother to do this, but I could just do that. So you know that this is Z3. This I mean W2. I'll do it this time, but I probably won't continue to do this. And this is here. So we have this equation, Z3 is that times that. So if we take the derivative of Z3 with respect to W2, that means this is the variable. So it's like this where it was x. Suppose I change this to x. So it's x times this. So this is a constant. So the answer is, of course, that this thing, the derivative here, is just the A2 here. So that we could say that this dj dw2, which is what we want, is this delta, which we sort of think of as a constant, because, well, we sort of think of it as a constant times A2. So we can, if we do think of this as a constant, then we would say that this is just that constant times A2. So we could say that this depends on A2. And in other words, if A2 is bigger, then this will be bigger. And if A2 is smaller, then this will be smaller. And this is the derivative that we're seeking. It's the derivative that's going to allow us to update weights. And so the update that we need, we could say that the update that we're going to need to do is dependent on the size of the input at that point. So let's take a look at that. So the update that we're going to do, remember dj dw2, that's going to tell us how much to update or get the W2 to get the new W2. So that update is going to depend on how large this was. So that's often what's said in this setting. So we'll say that the update here is a function of, or is dependent on, the size of the input at this point. Okay, so anyway, here's the formula. And we said if we think of this part as a constant, and this resolves just to A2, so we get this constant times A2, and that's what the derivative for W with respect to W2 will be. Okay, there's one other point I want to make here, and that is, notice that we said that y hat is f of z3. In other words, we take this z3 and we put it into f. Remember, f is the sigmoid function, and we get an output which we can either call a3, we said, or y hat. So here we're calling it y hat. So anyway, y hat is f of z3. Remember, f is the sigmoid function. Now we're going to need the derivative when we talk about doing the chain rule of j with respect to W2. We're going to bump into the derivative of f with respect to z3 here. Here, this is where you see it. Y hat, which is f of z3. This is the f part here, actually. With respect to z3, that is asking for the derivative of f with respect to z3. So that means we need the derivative of the sigmoid function. Now, earlier in the text, we went through some calculation. It may have been optional, or I think we showed the derivative of the sigmoid function. And we showed that the derivative of the sigmoid function, you can just ignore this inside part, just imagine it was x here. The derivative of the sigmoid function is the sigmoid function times 1 minus the sigmoid function. So that's a very nice expression of the derivative, but we're not going to use that. We're just going to code our sigmoid function like this. So sigmoid prime, so we're not going to write sigmoid prime in terms of sigmoid. We just, we can also write it like this. You can actually express the sigmoid function and do its derivative, and you get this for the derivative. So this is what we're going to just do this, and call it sigmoid prime. So we're actually not going to use this relationship, but we will need sigmoid prime. It is called for in the calculations of dj dw2. In fact, it's called for in the calculation of the delta 3, and then it's also called for in the calculation for the delta 2. So we will need it, but we're just going to do it here in this way. We're going to just code it like this. Okay, so now let's focus on the derivative of j with respect to w1. And we saw this was further upstream. w1 is further upstream here. And so to take the derivative of j with respect to w1, we're going to have to go through more processes. So the chain rule is going to have more terms in it. But all the terms that were in the derivative of j with respect to w2 will be basically in here, except for the last term, the one that we said we left out of the delta 3. That one term won't be in there, but the others will. All the ones in delta 3 will also be in this calculation. But anyway, the thing I want to say here is that it's going to be a longer calculation, but we also want the derivative of j with respect to w1 now. We need to do that because that's what we're going to use to update w1. So here it is, it's longer. And we're going to factor out all of these terms and call that delta 2. So we'll be able to say that this is delta 2, this part, times this one. And then we're going to have a very similar result like we had up here. Whoops, down. Like we had here when we do the derivative. When we do the derivative of this thing, it turned out just to be a2. We're going to have a very similar result next. So if we're going to do this derivative, last time we wrote j simply as a function of w2. We didn't push a2. We didn't force ourselves to express a2 in terms of w1. Of course, a2 is a function of w1, but we just left it like this. But now we need to write a2 in terms of w1, which is here's what we did. xw1 is the definition, f of xw1 is the definition of a2. In other words, xw1 is z2, and then if we put z2 into f, we get the a2 here. So anyway, we need to express j in terms of w1 if we want to calculate the derivative of j with respect to w1. So we have to do this. And this is the way it looks. You can confirm that for yourself. But anyway, we do need an expression for j in terms of w1. This is what we have. So now we can do the derivative of this whole thing with respect to w1. But as we said, it's sort of embedded in many functions. So that's going to call for many applications of the chain rule. And we have to do that. So this is the many applications of the chain rule. This is a result. It says we use the chain rule 6 times here, and that results in 7 factors. Then we could take, what was it, the first 4, 1, 2, 3, 4, I think those were the first 4. We called that delta 3. So we could take that and call that delta 3 still. Then we would say that this derivative is the delta 3. And then we still have some stuff left over. I think these 3 terms are left over. So we have the delta 3 and these 3 terms, but we're not going to stick with that. We're going to rather define delta 2, something else, as this times this times this. So we have delta 2 here times just this last term. And then again, if we think about this, maybe we should do it right now. Well, let's see what we do here first. So let's just see what happens here. Okay. So this is the result. So let me just go back here again. And so this whole thing is going to, this term, and this term all together are going to be called delta 2. So we're only left with this. And now let's think of what this is. So remember that we are doing the simplest neural network. That's a 1-1-1. So there's no matrices really involved here. And I guess I should bother to make this, do this and this, I guess, to make it look right. So that's then Z2 is just X, the input, times the first weight. There's no multiple nodes in the first layer, or there's no multiple nodes in the second layer. So it's just very simple. Z2 is just X times this. So that's what we have here. Now, if we take the derivative of Z2 with respect to W1, so don't think of this as the variable. Actually, usually we think of X as the variable, but here we're talking about the variable being W1. So don't think of X as the variable. In fact, think of this as like the constant. So the derivative of this thing, so if this is a constant with respect to W1, is just this thing, this X, this constant. So this term will just become X. So, and we said these, we're going to call these 3 here, delta 2. So this derivative, and this, remember, this is the thing that we use to update our weights. In this case, this is the thing we use to update W1. So this is critical, the most important calculation we do, as well as the one when we have a 2 here. That's equally as important. Anyway, this calculation turns out to be just this part, which we call delta 2, times this part, which we just saw, is X. So again, we get this same pattern where we say that the amount that we should update this weight is a function of the size of the input. The bigger X is, the more we have to update, the more we have to change W by. So that statement is supposed to have some kind of meaning, and I shouldn't admit it, but honestly, I'm not quite sure of the relevance of that. But it says that the amount that we're going to have to update this is somehow dependent or a function of the size of the input. The bigger the input, the more this has to be updated. And here is what we just said. Here's that expression. Here, the derivative of J with respect to W1 is this delta 2 that we've been talking about times, and we found out that the derivative was just X, just the size of the input. And so here's the updating scheme, but this doesn't have the R in it. We said that we actually will include an R, a learning rate we called it, which allows us to avoid, like suppose we're here and we get the derivative here, and the derivative will be quite steep here. I mean, the slope is quite steep here, so the derivative will be quite large. And if we were stuck with this formula for updating, and the derivative was very large, then this would say we have to make our new weight a lot different than our original weight, because this is going to change it by a lot, because this is the slope, and if the slope is really large, we're going to have to change this by a lot. But changing it by a lot, now we said that we noticed that when the slope was negative, our updating scheme would cause us to move to the right, which is what we want. But we're going to move to the right maybe to here. And so that may not be what we want. Now, in this particular picture, it might actually be a good thing. But if this was the absolute minimum here, and we moved over to here, that wouldn't be good, because then we'd say, oh, now next time we're going to move back over to here, and then we're going to move back over to here, and we may never get down to here. So we don't want to be stuck with having to update the weight by the full size of the derivative, because right here, as I said, the full size of the derivative could be quite large because this is quite steep. That means the derivative would be large, and we may not want to be stuck in that with that limitation. So we said we were going to throw in this R. That's called the learning rate. But it's just some constant that we can set. Now, when I said that we can set, so we could go through and train our neural network. We pick a particular R and see how well it does, how well the resulting neural network after being trained performs. Then we could say, oh, well, that R maybe wasn't so great. Let's try a different R. And maybe we'll get a better neural network with that. So we can experiment with the R's, the so-called learning rates, and see if one of them gives a better final result. That is, the neural network that we end up training, the trained neural network works better with new data than with some other R. Okay, so next we want to deal with the same thing that we just did, but we want to deal with it when we have this kind of architecture. So we're going to have, we still want to know how to update the weights. We're still going to just take the derivative of j with respect to this weight to know how to update this one. And in fact, for this network, it's going to be exactly the same at this point. To update this weight is going to be the same as it was before because there's nothing new downstream in this network than we had when we had the 1-1-1 network. So this way, there's nothing new. It's just going to be exactly the same stuff that we just did. But here it's going to be slightly it's going to be different, could be very different, but it doesn't turn out to be very different. It's going to be just a little bit different. But we'll still want to know how to update this weight and how to update this weight.